Alright, in this video we will work through an example problem using the equivalent resistance method. So if you are given a more complex network of resistors and, for example, asked to solve for the current, voltage, or power of a single resistor, how can you do that using what you've learned so far, primarily Kirchhoff's current and voltage laws and the rules for combining resistors in series and parallel. So let's start by drawing out the circuit we're going to analyze here. Oops, I want this to be white. We are going to have a battery connected by two resistors to two other resistors that are in parallel, and then another resistor back to the battery. So we're going to assign values to these resistors. We're going to call that R1 is 1 ohm, R2 here is 8 ohms, R3 is 7 ohms, and R4 down here is 500 milliohms. Now, these are just kind of made up numbers for this example, but you could think of this as a battery that is connected to two loads in parallel by some long wires. So notice how the resistance of these wires is a little lower and the resistance of these two is a little higher. So this could be something like a incandescent light bulb or a resistive heating element, and then you have the smaller but non-negligible resistance of the wires. And we are going to ask you to solve for the power, voltage, and current of R2. So we want all three variables there. So what is P2, what is V2, and what is the current I2 through that resistor. So our goal is to analyze this entire circuit by combining the resistors, solving for the voltage and current values, using what we know, like Kirchhoff's current law and Kirchhoff's voltage law, to ultimately find those parameters for just this resistor. And we are going to do that, as the title of this video implies, using the equivalent resistance method. So we are going to combine all of these resistors into a single equivalent resistor, solve for the voltage and current there, and then backtrack as we expand the circuit back out to the individual resistors. So I think it is easiest just to show that by working through the examples. So the first thing we're going to do, and with more complex circuits, there may be more than one way you can do this. I'm just going to work through one possible way of doing it here, is we are going to combine R2 and R3 because they are in parallel. So I'm going to draw a dotted line around them here to indicate that those two resistors are in parallel. If you're not sure what in parallel means, you need to go back and watch one of the earlier videos. So in this condensed version of the circuit, we still have R1 and R4 as separate resistors, but we have a new variable here that I'm going to call R23, which is equal to R2 in parallel with R3. That's shorthand notation for writing out that longer form of the equation you should be familiar with. 1 over R23 equals 1 over R2 plus 1 over R3. So rather than writing out this entire big equation, I'm just going to make up this new variable R23 to represent that equivalent resistance. My next step is that I am going to combine all three of these resistors in series. So now I know that, I'm going to draw this with a dotted line, these three resistance values are just in series, so I can combine this circuit all down to a single resistor. And I'm just going to call this value REQ, my equivalent resistance, and resistances just add in series, so that is R1 plus R23 plus R4. And I should have mentioned, I am just working through the whole thing symbolically here, even though I gave you numbers for this problem, because this lets you work through the entire problem, get a symbolic answer for your final calculations, and then plug in numbers. If you start plugging in numbers right away and you make a mistake, that mistake is going to propagate the whole way through your problem, and you don't want to do that. So it's always better to work through it symbolically first, and then if you make a mistake at the end, you just quickly redo your final calculation instead of having to go all the way back to the beginning. Okay, and now I am going to start applying Ohm's law. So I always know that Ohm's law is V equals IR, and I just realized I forgot to label a variable for my voltage. So let's call that battery as VS for my source voltage. So in this case, I have VS equals IREQ, where I is the current through that resistor. Now, here is where I can now start working backwards and using the information I have here. So remember, in this equation, my only unknown is I. I know Vs, that's a given. Let's call it, I don't know, 6 volts. And I know all of my resistance values, so I can calculate Req. So my only unknown in that equation is I. And I'm going to erase this to make a little more room to try and keep all of this on one slide here. Let's rewrite that a little smaller. So 1 over R23 equals 1 over R2 plus 1 over R3. So we are now going to take this circuit and expand it out again back up to this step. So we're going to have Vs, which is 3 volts. We're going to expand back out to our 3 resistors in series. Relabel those values. We had R1, R4, and R23. But now we know these resistors are in series and the current through them has to be the same. So we know this current I. Again, I haven't calculated the numerical value yet, but I know that I is equal to Vs over Req, so I can calculate that. So I now know the current through each of these resistors. And again, according to Ohm's law, if I know the current through a resistor, I know the voltage drop across that resistor. So I'm going to make up some intermediate variables here. I'm going to pick these 2 nodes and say I'm going to call this one VA, and I'm going to call this one VB for the voltages at those nodes referenced to ground. I haven't explicitly drawn the ground symbol in this circuit. Again, we have another video about that, but since we just have a single battery, it's implied that the negative terminal of the battery is 0 volts or ground. So I am going to make up, again, 2 more variables for these kind of intermediate nodes between the resistors so I can solve for the voltages there. And remember, while we're doing that, don't lose sight of our ultimate goal, which is finding the current, voltage, and power of this resistor here. So I know that the current through all three of these resistors is the same, and I know, as always, Ohm's law, V equals IR. I can solve for the voltage drop over any individual resistor if I know the current through that resistor. So in this case, for example, I know that if I have 0 volts down here, I have Vs up here, I have the drop over R1, and that is going to give me VA. So I can write an equation, VA equals Vs, and this is applying Kirchhoff's voltage law, or informally that voltages add or drop in series, depending on whether the sign is positive or negative. VA equals Vs minus what I'll call VR1, where this is the drop over R1. Remember, again, we have a different video about this. There's a difference between labeling a voltage at a single point where you are implying that it is measured reference to ground, or calling the voltage drop across a resistor, which in this case is going to be the difference between Vs and VA. So that is not reference to ground. It is between these 2 points. So I have VA equals Vs minus VR1. And again, according to Ohm's law, I know that that VR1 is going to be equal to, oops, that should be a minus, I R1, and remember that this I is the same one I solved for way over here. So again, I'm not solving for any numerical values yet. I'm keeping this all symbolic. So you just have to keep track of the algebra, then that makes your life way easier at the end of the day. So I've solved for VA. I now know the voltage here, because again, remember, I know everything else in this equation. I know R1, I know Vs, and I solve for I over here. I can do the same thing for VB, which is going to be 0 volts plus the voltage drop over R4. So 0 plus VR4. I wrote the kind of redundant to write 0 plus something there, but I'm writing it just to be consistent to show that we're adding the voltage from this point to get the voltage over at that point. And VR4 is again just going to be Ohm's law. That is going to be IR4. And again, that's the same I that I had up in this equation because all 3 of these resistors are in series. Okay, so now again, I'm still writing everything out symbolically, but I have a bunch of variables here that I can calculate the numerical values for. I know I know VA, and I know VB. I can now take the final step of expanding my circuit back to its original form with all 4 resistors separate, like this. So there's R1, R4, R2, R3, And you'll notice what I don't know anymore is the current through R2 and R3. So here, when I had merged those into a single resistor, I knew that the current through all of these had to be the same. So here, that current through R1 and R4 still has to be I, because that's going around the loop. But then here it splits. Remember Kirchhoff's current law. This is going to split. I'll call that I2 and I3. I2 and I3 merge again at this point. So I can write an equation using Kirchhoff's current law that I equals I2 plus I3, but those are unknowns. I do not know those. What I do know from my previous step, though, is that I still have VA and VB at these two nodes. So here you kind of have a choice of what you can do based on what you were asked to solve for. Remember that I was asked to solve for the parameters of interest I2, V2, and P2 for R2 here. And I actually have the information I need to do that because since I've solved for VA and VB, I know the voltage drop across this resistor. That means I can solve for the current through this resistor, and I can also get the power across this resistor. So the voltage across the resistor, we'll call that V2, is simply going to be VA minus VB. And then the current, according to Ohm's law, V equals IR. We can get the current. I2 equals V over R, and then remember there are a couple different forms of the power equation, so you can kind of use whichever one you want. You could do P equals IV, which also equals I squared R, which also equals V squared over R. So you have all those variables. You can use whichever one you want to calculate the power. So on the next slide, I'm going to copy over all of the known values in all of these equations, and we will actually chug through and get the final numerical answer for V2, I2, and P2. All right, so here I have copied over everything we had on the previous slide to give us a clean slide for the math. So we have our knowns, or our given values, the voltage of the battery, and the four resistances. We have our unknowns, or what we were asked to solve for, I2, V2, and P2. And then we have a whole bunch of equations, and I've kind of written these in the reverse order of which we derive them. So we have these final equations here that will give us V2, I2, and P2, but we have a bunch of intermediate equations we need to solve for first. So these equations depend on these VA and VB variables. In order to solve for VA and VB, we need that current. In order to solve for the current, we need the equivalent resistance. And in order to solve for the equivalent resistance, we need to apply our rules about resistors in series and parallel. So to actually solve this, we're going to start back here with equation 7 and work our way up towards equation 1. Actually, I'm sorry, let me correct myself. At this point, you kind of have a choice. You can start here and start plugging in numbers and solve for the intermediate variables and work your way this way. The risk in doing that, again, is if you make a mistake early on, then that mistake is going to propagate all the way through to your final answer. You can also do more algebra and combine these equations to just get a single equation that gives you an unknown as a function of things you know, and then plug them all in at once. So I'm going to choose the latter approach here. We're going to show solving for these equations again in terms of things we know, so you can just punch it all in terms of one calculation, and then if you make a mistake, it's easy to just do that one calculation over again instead of doing sequential calculations over again. If you're not comfortable doing that and you don't like merging all of these equations with the algebra, then you can kind of plug in the numbers one at a time. So you would use this equation to solve for R23, then you would use this equation to solve for REQ, then you would use this equation to solve for I, use these equations to solve for VA and VB, and then you could go over here. Again, just the risk you carry if you do that is if you mess up this one, then your intermediate answers for all of these are going to be wrong, and then you have to go back and do the whole thing over again. So instead, what I'm going to show is combining these equations just to hopefully get a single equation. So for each of the variables we're interested in. So let's start out with V2 equals VA minus VB. Now we're going to plug in, substitute in equations 3 and 4 for our values for VA and VB there. So that's going to be VS minus I R1. Then minus VB is minus I R4. So again, here we're getting into algebra. You could choose to simplify this if you want to. So you could write VS minus I times the quantity R1 plus R4. Be careful with your signs when you're factoring things out. And now we're going to substitute equation 5 in for I. So that's going to be Vs minus Vs over Req times R1 plus R4. And again, here you have a choice of whether or not you want to factor out that Vs. So that could be equal to Vs times 1 minus 1 over Req. Oops. Times R1 plus R4. So now we almost have everything except for that Req value. So you could take an intermediate approach and say, I don't feel like writing out a giant equation with all of this Req stuff, so maybe solve for the Req value first and then just use this equation, but I am, for the sake of chugging through the whole thing, I'm going to do the whole giant equation here. So that's going to be Vs times 1 minus R1 plus R4 all over, now we're going to plug in equation 6, so that is R1 plus R23 plus R4. And this is where, again, maybe combining equations makes the algebra kind of annoying because of how big and nasty that formula for resistors in parallel gets. So that's going to be Vs times 1 minus R1 plus R4 all over R1 plus R23, which, if we substitute in equation 7, is 1 over R2 plus 1 over R3 to the minus 1 plus R4. So there we go. I have a single giant equation that should give me V2. So we can go ahead and substitute all the numbers in for that. That's going to be 6 times 1 minus R1 is 1 ohm, plus R4 is, that was listed as 500 milliohms, which remember is half an ohm, all over R1, which is 1 ohm, plus 1 over R2, so that's 1 over 8, plus 1 over R3, 1 over 7, that to the minus 1, plus R4 again, which is 0.5. All of that, let's plug that into the calculator and see what we get for V2. And after plugging all of that in, I get an answer with a little bit of rounding of 1.72 volts for V2. And as a quick sanity check, that is not greater than 6 volts, so there's no active elements or external separate power supplies in this circuit. So if I got more than 6 volts, that would be a problem. And I didn't get a negative number, so I know that I shouldn't have, unless I had defined my sign convention wrong, which I didn't really bother with in this circuit, I shouldn't get a negative voltage either. So at least I know that this voltage is physically possible. I can then go along and solve for my I2, which is V2 over R2, which is going to be my 1.72 volts over 8 ohms. And for that, I get a value of 0.21 amps. And then finally, I can go ahead and solve for P2. I'm going to use IV equals 1.72 times 0.21 amps. And that gives me 0.36 watts. So, assuming I did not make a mistake in my algebra or my math, which you are free to check me on and leave a comment if I am wrong, I have now solved for the 3 variables that I asked you to solve for initially. I think I am going to go ahead on the next slide and also double check my math by doing this with the other technique I mentioned, which is working backwards with the equations and solving for numerical values at each step, which again carries the risk of propagating an error, but as you can see, the risk with this approach is that the algebra can get kind of messy, especially once you start dealing with all the resistors. So clearly, if you mess up your algebra, then it doesn't matter if you have a single equation at the end to plug numbers into if this equation is wrong. So matter of personal preference and how you're comfortable with math. If you find one approach easier than the other, that is fine. For the sake of checking my own answers, again, in this video, I'm going to go ahead and try the other method as well and make sure that I get the same answers. And oops, I just realized that on this slide I labeled 2 number equation 3s, so hopefully that was still made sense with what I did, and this should have been equation 8 over here, but I labeled which ones I was substituting, so hopefully that wasn't too confusing. Anyway, I have now, my slides went to advance, copied over the same stuff on the next slide, and we are going to go through and just plug in everything numerically and solve these one step at a time. So R23 is going to be equal to 1 over R2, which is 8, plus 1 over R3, which is 7, all to the -1. And if I plug that into my calculator, I get 3.73 ohms. So that was for equation 8. I'm now going to, terrible 8 there, move on to equation 7. Req is going to be R1, which is 1 ohm, plus R23, which I just solved for, which is 3.73 ohms, plus R4, which is 0.5 ohms. So when I plug that in, I get 5.23 ohms. And sorry, do as I say, not as I do. Don't get lazy about units. You don't want to lose track. Again, this problem's pretty easy because they don't have any millis or killas in there, but you don't want to lose track of your units because that can mess up your calculations. Okay, so I have my REQ. I am now going to go on to equation 6. I equals Vs over REQ, so that's going to be my 6 volts over my 5.23 ohms. And when I plug that in, I will get 1.147 amps. Great. Let's move on to equation 5. VB equals I times R4. So that's going to be 1.147 amps times R4, which is 0.5 ohms. Plug that in, and we get 0.573 volts for VB. I'm going to go up to equation 4 for VA. We're going to get, whoops, VA is Vs, which is 6, minus I, which is 1.147, times R1, which is 1 ohm. So 6 minus 1.147, and that gives us 4.853 volts for VA. So now we can finally go jump up to equation 1 and solve for V2, which is going to be VA minus VB, so that is 4.853 minus 0.573, and that gives us 4.28 volts for V2. Let's go back and check if that matches what we got on the previous slide. It does not at all, so I made a mistake somewhere. This is a great example of why it is good to go through and check your work. Let's chug through and figure out what I did wrong. Actually, before I do that, let's go through and solve for the I and V or P values with this method. So I2 is going to be V2 over R2, which is 4.28 over R2, which is 8, and that gives 0.535 amps. And then finally the power is going to be P equals IV, so that is 4.28 times 0.535, which gives 2.29 round this up, 29 watts. So power is much higher in this case. So again, I did something wrong in one of these approaches, which is exactly what I warned about. I either made an early on mathematical mistake here, which then propagated through the rest of the errors, or I made an algebra mistake here, meaning my final equation is wrong and the the resulting answers here are therefore wrong. I am going to sit here and double check my math and see if I can figure it out, but if you are watching this video and you have already spotted an error and you know which one of these is correct, please go ahead and leave a comment below the video. Let me know which answer you think is correct and where you have spotted the error. And not to worry, I found a mistake. When I plugged this equation into my calculator earlier, I forgot this 1 minus. So I only calculated this fraction over here and then forgot to subtract it from 1, which resulted in this incorrect answer for V2, which then, of course, propagated on to incorrect answers for I2 and P2. When you remember this 1 minus term, then thankfully you get the same answer of 4.28 volts for V2. And then you'll go on to get, again, here's that V2 value. You'll get the same answers for I2 and P2. So again, be careful either way. It only takes one missed number when you're doing a bigger final calculation like this to mess up your final answer, even if your equation was correct. Or in this case, again, if I had messed up, for example, something here in step 7, then that would have propagated through all of the other ones. So if you're doing something like graded homework, or on an exam, if you have time, it always helps to use 2 different methods like this to check and make sure you get the same result, or just go through your same calculations twice from scratch and make sure you get the same answer the second time. Now, you might have noticed or developed the feeling that all of this was kind of a pain for what initially seemed like a very simple circuit. It kind of did require slogging through a lot of step-by-step algebra. We can get around that if you know linear algebra with two different techniques called mesh and node analysis that allow you to solve for a system of equations that describe the entire circuit and then use either a graphing calculator or MATLAB or anything else that can solve, do matrix algebra to solve for all of your unknown variables of interest at once instead of slogging through line by line and doing a bunch of algebra by hand like this. So that can save you a little bit of effort if you are familiar with linear algebra, which again, you usually haven't seen at the high school level, but would probably see at the college level. So in the next couple of videos, we are going to explore using those techniques instead.